Welcome to the deep dive. We take complex stuff, break it down, and hopefully make it really engaging knowledge for you. Today, we're diving into something truly epic. A journey that took, over a decade? And cost billions. The Rosetta mission to Comet 67 Churyumov-Gerasimenko, just spectacular and pretty dramatic, too.
Oh, absolutely. A colossal effort. 12 years from launch in 2004, right through to that final signal in September 2016. We're really talking about the most ambitious, the most detailed look at a comet ever attempted. You had the Rosetta orbiter, of course, and then its passenger, the Philae lander, which, well, it had its share of troubles, but still incredibly successful in the end.
And the names themselves, Rosetta and Philae, they weren't just picked randomly, right? They signaled the mission's whole purpose.
Exactly. Like the Rosetta Stone and the Philae obelisk helped us decipher ancient Egyptian hieroglyphs.
Right.
This mission, the idea was it would help us decipher the hieroglyphs of the early solar system, secrets frozen inside that comet nucleus.
Cosmic history, basically.
Precisely. And the sheer audacity of it all led to some major firsts. I mean, first spacecraft ever to properly orbit a comet nucleus. That alone was huge.
And the landing.
And Philae, despite the drama, achieved the first ever soft landing on a comet. Okay, yes, there were some high-speed bounces involved immediately after.
Yeah, just a few.
But making that initial contact, that was groundbreaking science and engineering right there.
Absolutely. So that's our goal today in this deep dive. We want to take all that amazing engineering, the nail-biting moments of the landing, the incredible science that came out of it, and distill it down for you. We'll unpack the whole journey, starting with just how long and complicated it was for Rosetta to even get there. Okay, so launch, March 2nd, 2004. Ariane 5G plus rocket, everything goes smoothly off the pad. But almost immediately, there was a big change needed, something about the target.
Yeah, that's right. The original plan, the mission was initially aimed at a much smaller comet, 46P Vertinen, but there had been an earlier unrelated failure of an Ariane 5 rocket, which caused delays. Big delays. By the time Rosetta was actually ready and clear to fly, the launch window, the specific time they needed to leave Earth to intercept 46P, that window had closed. Gone.
So they had to scramble.
They had to pivot fast. The backup target was 67P Churyumov-Gerasimenko. But it wasn't just a simple name change on the mission plan. 67P is significantly larger than Vertinen, bigger mass, stronger gravity, which meant the lander, Philae, would likely hit the surface harder.
So even before launch, they were already redesigning parts.
Exactly. Engineers had to go back and strengthen Philae's landing gear to cope with that potentially rougher landing scenario. It really set the tone, Adaptability was key from day one.
And then the journey itself, nearly 4,000 days just cruising.
Yeah, 3,907 days to be precise. It was a monumental cruise phase. See, Rosetta couldn't just fly straight there. It launched on a relatively slow path. It needed to use gravity assists, slingshotting around planets to build up enough speed to reach 67P way out in the outer solar system.
Yeah.
That required incredible navigational precision.
We hear about gravity assists a lot, but Rosettas were pretty complex. 3 Earth flybys.
3 Earth flybys, yeah. 2005, 2007, and 2009. Each one adding velocity. And that second one, the 2007 flyby, that had a funny little story attached to it.
Oh, yeah. What was that?
Well, as Rosetta zipped past Earth, some astronomers doing routine sky surveys, they actually spotted it through their telescopes. For a short time, they thought they'd discovered a brand new near-Earth asteroid. They even gave it a temporary designation, 2007 VN84.
Oh, way.
Yeah, until someone realized, wait a minute, that trajectory looks familiar. That's our spacecraft. Just shows how fast and far out it was already.
And speaking of speed and risk, there was that Mars flyby in 2007, dubbed the billion-euro gamble. That sounds intense. Why so risky?
Okay, so the path itself took Rosetta just 250 kilometers over the Martian surface. That's incredibly close, designed to get the maximum gravitational kick.
Super close shave.
Right. But the real danger wasn't hitting Mars, it was the darkness. Rosetta flew directly through Mars' shadow for a full 15 minutes.
15 minutes?
Yeah.
Completely cut off from sunlight, relying only on batteries.
Exactly. The solar panels, its main power source, were totally useless in the shadow.
Yeah.
And the batteries, well, they weren't really designed for that kind of deep discharge during a critical maneuver. If those batteries had failed to keep the essential systems alive during the blackout or couldn't recharge properly afterwards, poof, mission over. Billions of euros potentially lost right there.
Wow.
Thankfully, it worked perfectly. Came out the other side, recharged, and even grabbed some bonus science, great images of Mars, atmospheric data.
Yeah.
But yeah, definitely a high-stakes gamble.
And it wasn't just planets. Rosetta used its long trip to check out some asteroids too, right? testing the instruments.
It did. Scored a couple of European firsts there. September 2008, it flew past asteroid 200 and 867 Hattanes. Got really close, less than 800 kilometers. Then, July 2010, it encountered a much larger main belt asteroid, 21 Lutetia. Flew about 3,168 kilometers away that time.
Lutetia was a big one, wasn't it?
Yeah, quite chunky. The flyby gave us amazing images, resolution down to like 60 meters per pixel, mapped about half its surface. These weren't just sightseeing detours. They were crucial for calibrating the cameras and spectrometers, the instruments that would eventually study 67P up close.
Okay, so flyby is done, speed built up, but then came a really long, quiet period, deep space hibernation.
Absolutely critical. Rosetta was heading way out, far from the sun where solar power gets weak. So, starting June 2011, they put it into a deep sleep. It was spin-stabilized, almost everything non-essential shut down, just sipping power for 31 long months. The plan was for an internal alarm clock to wake it up automatically in January 2014.
But deep space travel isn't gentle, is it? Things can go wrong even when a spacecraft is asleep.
Takes a toll, definitely. And when Rosetta woke up, the team discovered a couple of serious technical headaches they had to deal with while still cruising towards the comet.
Uh-oh. What kind of problems?
Two main systems were acting up. First, the reaction control system, that's the network of small thrusters, used for fine-tuning the spacecraft's position and orientation. They found a leak.
A leak? That sounds bad.
It was a concern. They were pretty confident they still had enough fuel, enough propellant, to finish the mission. But it meant the system had to operate at a lower pressure, which needed careful management. But the really worrying issue was with the reaction wheel assemblies, the RWAs.
Ah, the spinning wheels that help point the spacecraft without firing thrusters all the time. What was wrong with them?
They started showing signs of, well, serious bearing friction noise. Basically, imagine a spinning disc inside. If the bearings that let it spin smoothly aren't lubricated properly, friction builds up. It gets noisy, inefficient, and can eventually seize up completely. Catastrophic failure. After the Atteens flyby, one wheel, RWA-B, was already shut down because the noise was just too bad. Then another one, RWA-C, started acting up significantly too.
So you've got this billion-dollar probe hurtling through space, and its steering mechanism is starting to grind itself apart. How do you even begin to fix that remotely?
It was an incredibly clever bit of engineering, actually, real ingenuity. The team figured out that if they deliberately, temporarily increased the operating temperature of the reaction wheels.
Heated them up.
Yeah, gently. The idea was that the slightly higher temperature would encourage the lubricant, the oil inside the bearings, to sort of flow and redistribute itself more effectively, kind of like giving the bearings a warm oil massage from millions of kilometers away.
That's amazing.
It really was. They also used data from ground tests on a spare RWA during the hibernation to refine the strategy. When Rosetta woke up, they applied fixes, including limiting the maximum operating speed of all the wheels to below 1,000 RPM. This careful management allowed the wheels to keep working, even with the heavy demands of all the braking maneuvers needed to finally arrive at 67P. It just shows incredible adaptability from the ground team.
So after that incredible 10-year journey, the asteroid flybys, surviving hibernation, fixing those reaction wheels, Rosetta finally starts the approach phase in May 2014. Time to slow down and meet the comet.
Right, this was the critical transition. When Rosetta first got close, it was still zooming along at 775 meters per second relative to the comet. That's like, what, over 1,700 miles per hour?
Right.
Way too fast to just pull up alongside.
Yeah, you can't just hit the brace in space.
Exactly. So over the next 3 months, May, June, July, Rosetta performed a series of 8 precisely calculated deceleration burns. Little nudges from its thrusters. Each burn slowed it down relative to 67P, until finally, that relative velocity was down to just 7.9 meters per second. Slow enough for the final orbit insertion burn on August 6th, 2014. They'd arrived.
And that's when we all got our first really good look at 67P. And it wasn't exactly a smooth, round snowball, was it?
Not at all. The OSIRIS camera images confirmed it almost immediately. It's incredibly irregular shape. People started calling it the rubber ducky, or maybe a boulder club. 2 distinct lobes connected by a thinner neck.
Which must have made choosing a landing spot for Philae incredibly difficult.
Oh, unbelievably complex. With a shape like that, the center of mass is where you'd expect it to be. The gravitational field is, well, it's lumpy, erratic. So picking a landing site wasn't just about finding a flat-ish area. It was about finding a spot where the local gravity was predictable enough that Philae could actually target it and hopefully land without just sliding off sideways.
After all that analysis, where did they decide to aim?
In September 2014, ESA announced the primary target, Site J, located on the smaller of the two lobes. And then they held a public naming contest.
Ah, right.
Yeah, and Site J was officially named Agilkia Island. Keeping that Egyptian theme going, Agilkia is the island on the Nile where the Philae temples were eventually moved to save them from flooding.
Nice touch. Okay, let's talk Philae's design for landing. This is the tricky part. The comet's gravity is so weak, the escape velocity is tiny, like walking speed. How is Philae supposed to stick the landing?
The physics are just crazy. Philae was designed to touch down gently, maybe around 1 meter per second. That's about 3.6 kilometers per hour, barely a brisk walk. The problem is, even that gentle touch could cause it to rebound straight back into space, because the escape velocity is only slightly higher, maybe 1 meter per second itself, maybe less, depending on location.
So it needed anchors.
Desperately needed anchors. It had a two-part system. First, built into the landing legs were ice screws designed to bite into the surface immediately on contact. Second, and this was the main anchoring system, were two harpoons. These were supposed to fire downwards the instant touchdown was detected, shooting out at about 70 meters per second to really embed themselves deep into the cometary ice and pin the lander down.
But wait, firing harpoons downwards, wouldn't that push the lander up, like recoil?
Precisely the problem. The recoil from firing those powerful harpoons would absolutely be enough to overcome the comet's weak gravity and send Philae bouncing off. So the design included a crucial countermeasure. A small, cold gas thruster mounted on the top of the lander.
Ah, to push it down.
Exactly. It was programmed to fire at the exact same moment the harpoons deployed, providing a continuous downward force to counteract the recoil, press Philae firmly onto the surface, and make sure those harpoons got a good grip. It was essential.
Which leads us right to that heart-stopping moment just before separation. They discovered a major flaw, didn't they? Something unfixable.
Yeah. The critical piece, that downward-firing cold gas thruster, wasn't working. During one of the final systems checks, just hours before Philae was supposed to detach from Rosetta on November 12, 2014, they confirmed it. Non-functional.
And no way to fix it out there.
No chance. So Mission Control faced this absolutely brutal choice. Scrub the landing attempt entirely after a 10-year journey. Or push ahead. Proceed, knowing that the primary system designed to prevent the lander from bouncing off the comet was dead. Rely entirely on the harpoons getting a perfect grip without that downward push.
They went for it.
They made the incredibly tough call. They decided to proceed, banking everything on an absolutely perfect, feather-soft touchdown in exactly the right spot, hoping the ice screws and harpoons would somehow be enough on their own. A massive gamble.
Knowing the anchor system was compromised from the start, it makes what happened next feel almost inevitable, doesn't it? Less like a freak accident.
Definitely changes the perspective. The engineers knew the risks, knew the physics. The drama just ramps up exponentially.
Okay, November 12th, 2014, Philae separates from Rosetta, begins its long, slow, 7-hour fall towards Agilkia, just drifting down. And then the signal, touchdown confirmed, 15.34 UTC. Success. Or maybe not quite.
Well, that first signal confirmed contact. But almost immediately, telemetry started showing something was wrong. The chaos began. What unfolded was that triple touchdown drama and the failure mechanism. It was exactly what they'd feared without the top thruster. Analysis later confirmed, yep, the thruster didn't fire. And worse, the landing was actually so soft, so gentle, that the impact sensors didn't register enough force to properly trigger the harpoon firing sequence. The harpoons never deployed.
So it landed perfectly. Too perfectly, and had no anchors.
Exactly. A beautiful soft landing that instantly set it up for failure, and then it bounced.
How high did it go on that first rebound?
That first bounce was the really terrifying one for the team back at Mission Control. It rebounded upwards at 38 centimeters per second. Now remember, the escape velocity on that part of the comet was estimated around maybe 44 centimeters. It came incredibly close to just floating away forever.
Wow.
It drifted upwards for about 1 kilometer, a full kilometer above the comet's surface.
Tumbling through space above a comet, unguided. For how long?
That first flight lasted almost 2 hours. And during that long, slow arc, the data suggests Philae actually clipped something, maybe the edge of a cliff or a large boulder on the surface. That impact sent it into a slow tumble. It was rotating about once every 24 seconds as it drifted.
Unbelievable. When did it finally come back down?
It touched down a second time, nearly 2 hours after the first contact, at 17.25 UTC. It bounced again, but much smaller this time, only about 3 centimeters rebound. And then moments later, at 17.31 UTC, it finally came to a complete stop. But the place where it stopped, well, that presented the next huge problem.
It wasn't on the nice flat spot they'd aimed for, was it?
Not even close. The final resting place turned out to be an incredibly rough, uneven terrain. The lander was tilted at a precarious angle, about 30 degrees. Miraculously, the structure itself seemed okay, nothing major broken. But the location, that led straight into the power crisis.
Right, because it landed in shadow.
Catastrophically so. They eventually figured out, and later confirmed visually, that it had ended up wedged in a dark crack or crevice, probably in the shadow of a large cliff or crater wall in a region called Manat. Instead of the open sunlight it needed to charge its secondary long-life batteries via the solar panels, it was only getting about 90 minutes of weak, indirect sunlight during each 12.4-hour comet day.
90 minutes, that's nowhere near enough.
Nowhere near. It doomed any chance of long-term operation. The primary battery, the one it launched with, only had about 60 hours of life in it from the moment of landing.
So, a ticking clock. 60 hours to get as much science as possible before the lights went out. What did they prioritize?
It became an immediate frantic scramble. The science teams and mission controllers worked around the clock. They commanded Philae to execute as much of the planned initial science sequence as possible, about 80% of it, remarkably. This meant deploying instruments like MUPUS, the penetrator hammer,
Right.
and SD2, the drill, and running the chemistry labs, Keosak and Ptolemy, to sniff the environment. They knew they only had maybe 2.5 days.
And they tried one last thing, didn't they? A little nudge to try and catch more sun later.
Yeah, a final desperate measure.
Yeah.
In the very last communication session, just before the primary battery finally died, they sent a command sequence. Philae actually managed to lift itself up by about 4 centimeters and rotate about 35 degrees. The hope was this might angle its main solar panel slightly better towards where the sun would be in the sky as the comet got closer to the sun on its orbit. A long shot.
Did it help?
We'll get to that later, but the immediate effect was nothing. The power levels just kept dropping. Contact was officially lost early on November 15, 2014, around 0.36 UTC. Philae went into hibernation. A heroic couple of days, but ultimately very short-lived.
Okay, so the landing was chaotic, the power situation was dire. But despite all that, the science Philae managed to grab in those 60 hours, plus all the ongoing data from Rosetta orbiting above, it really changed our understanding of comets, didn't it?
Absolutely revolutionized it. Even in those first couple of days, one of the biggest immediate surprises was just how hard the surface was.
Right, everyone thought comets were supposed to be like fluffy snowballs.
That was the prevailing model, yeah. Soft, porous, easy to poke into. But the data from Philae's instruments told a completely different story. At that first touchdown spot, a Gilkia, the Sesame instrument package, which measured acoustic and seismic properties, indicated something much tougher. It suggested a layer of granular dust or regolith, maybe 25 centimeters deep, covering surprisingly strong water ice.
Not fluffy at all.
Yeah.
And what about the final resting place where it got stuck? Was it hard there too?
Even harder, it seems. The MUPUS instrument, that's the one with the hammer probe designed to penetrate the surface.
Yeah, the little jackhammer.
Right. Well, even when controllers remotely commanded it to hammer with increasing force, it just couldn't penetrate very far at all. The analysis suggested the consistency was more like solid, dense ice, or maybe even something like pumice, very hard, porous rock. This really forced a rethink of how comets form and compact in the early solar system.
And that hardness, presumably, is why the drilling didn't quite go as planned either.
It certainly explains the difficulties. The SD2 drill, the sample drill and distribution system, was commanded to perform its full sequence. Drill down, collect a powdered sample, deliver it to the little ovens on board for the Keosak and Ptolemy instruments to analyze. It went through the motions, the mechanisms worked. But because the surface was so unexpectedly hard and icy, it seems the drill wasn't able to actually collect and transfer a proper sample into the ovens. They remained empty.
Ah, that's a shame. A major mechanical disappointment there. But the instruments still managed to detect some incredible chemistry, right? Even without a drilled sample.
Yes, and this is where the bouncing landing, ironically, might have helped a bit. The impacts plus the drilling attempt stirred up a cloud of dust and gas right around the lander. And the two main chemistry instruments, Keosak and Ptolemy, basically sophisticated mass spectrometers, they were able to sniff that disturbed material. And the results for organic chemistry were, frankly, spectacular.
What did they find?
16 distinct organic compounds were identified, just from that initial analysis around the lander. Molecules containing carbon, hydrogen, oxygen, nitrogen. The basic building blocks.
Were there any totally new discoveries among them? Things never seen on a comet before?
Yes, 4 of them were first-timers for comets. Acetamide, acetone, methyl isocyanate, and propionaldehyde. Now, these might sound obscure, but finding these kinds of complex organic molecules is huge. They are known precursors, intermediate steps in the chemical pathways that can lead to things like amino acids, sugars, the very stuff life on Earth is made of.
So it really strengthens that whole idea of comets delivering the ingredients for life to early Earth?
It's strong evidence in that direction, yes. And it wasn't just Philae. Later on, the Rosetta orbiter, using its own powerful Rosetta spectrometer to analyze the gas cloud, the coma surrounding the comet nucleus.
Yeah.
It directly detected the amino acid glycine. Glycine is one of the simplest but absolutely essential building blocks for proteins. Finding it there was a massive confirmation. They also found precursor molecules needed to make glycine, like methylamine and ethylamine.
Glycine itself, and I remember reading something about its handedness, chirality.
That's a key detail. The glycine detected appeared to be non-chiral, meaning it didn't have the specific left or right-handed structure that biologically produced amino acids on Earth typically show. Finding non-chiral glycine strongly suggests it formed through natural, abiotic chemical processes out there in space or on the early comet. It wasn't contamination from Earth, and it shows these fundamental building blocks can arise without life already being present.
So space itself is cooking up life's ingredients.
That's what the evidence points to. These complex organics seem to be pretty common products of cosmic chemistry.
And Rosetta's Virtus instrument, the mapping spectrometer, it gave a picture of the whole surface composition too, right? Was it all icy?
Not really, no. Virtus showed that the entire surface, pretty much everywhere they looked, was coated in a dark layer. This wasn't just water ice. It was made of complex, non-volatile, organic macromolecular compounds. Think sticky, tar-like, carbon-rich solids, all mixed up with things like sulfides and tiny grains of iron-nickel alloys. This composition actually provides a really important link. It shows that the material in Comet 67P is chemically very similar to what we find in carbonaceous chondrite meteorites.
The really old primitive meteorites found on Earth.
Exactly. The most ancient carbon-rich samples we have from the early solar system. So 67P looks like a larger, potentially less altered chunk of that same primordial stuff. It paints a picture of comets being more like dark, organic, rich dirt clods than clean white snowballs. One interesting point, though. Virtus didn't detect any hydrated minerals, the kind you find in some water-rich asteroids or meteorites. That suggests maybe this family of comets formed under slightly different conditions.
Okay, fascinating stuff. But now let's get to maybe the biggest scientific roller coaster ride of the mission, the water story. The question of whether comets like 67P delivered Earth's oceans. Rosetta initially seemed to say no, but then that changed.
Oh yeah, this is a classic example of the scientific process in action. It all comes down to something called the deuterium to hydrogen ratio, the DH ratio. Deuterium is just a heavier version and isotope of hydrogen. Water is H2O. Sometimes one of those H atoms is actually a D atom. The ratio of D to H in water acts like a fingerprint, telling you something about where in the solar system that water formed. Earth's oceans have a very specific, quite low DH ratio.
So the initial measurement from Rosetta back in 2014, what did it find for 67P's water?
The first results, published in late 2014, were pretty definitive and surprising. They indicated that the DH ratio in the water coming off Comet 67P was 3 times higher than the ratio found in Earth's oceans.
3 times, so very different water.
Very different fingerprint. The conclusion at the time seemed clear. Comets from the Jupiter family, like 67P, could not have been the primary source of Earth's water. It just didn't match. This sent ripples through the planetary science community. It really shifted the focus towards asteroids as the more likely water delivery mechanism for early Earth.
But that wasn't the end of the story. There was a major correction years later.
That's right. Science is self-correcting, sometimes slowly. Years later, teams went back and did an extremely thorough reanalysis of the original mass spectrometer data from the Rosetta instrument. And in 2024, they published a correction. They identified a subtle but significant error in how the initial measurements were processed and calibrated.
An error in the calculation.
Essentially, yes. A systematic effect wasn't fully accounted for in the first analysis. When they applied the correction, the new, revised analysis concluded that the DH ratio of 67P's water is actually remarkably similar to Earth's ocean water.
Wow, so it completely flipped the conclusion.
Completely reversed it. Suddenly, Jupiter family comets like 67P were back on the table as potentially significant contributors to Earth's water budget. It was a huge turnaround, a real testament to the rigor of checking and rechecking results. And it makes the story of Earth's water origins even more complex and interesting.
That is absolutely fascinating.
Yeah.
Okay, beyond the organics and the water drama, what other weird, exotic things did Rosetta find? We have to mention the singing comet, right?
Ah, yes, the singing comet. That came from the magnetometer instruments on Rosetta. They detected oscillations in the magnetic field around the comet, happening at really low frequencies, around 40 to 50 millihertz.
Yeah.
When the scientists converted these magnetic field fluctuations into audio frequencies that humans can hear, it produced this strange, rhythmic, almost humming or singing sound.
Was the comet itself magnetic?
That was the initial question. But later, Philae's instruments on the surface confirmed that the nucleus itself doesn't have its own intrinsic magnetic field like Earth does. So the singing wasn't coming from the rock itself. It's generated by the complex interaction between the charged particles streaming out from the sun, the solar wind, and the neutral gas erupting from the comet's surface as it gets heated, a kind of plasma interaction symphony.
Cool. And the last big surprise, finding simple oxygen gas, O2. Why was that such a shock?
Finding molecular oxygen, O2, freely existing in the comet's coma was profoundly unexpected because O2 is extremely reactive. On Earth, it doesn't hang around long unless it's constantly replenished, like by plants. It wants to combine with other elements. Yet Rosetta found quite a lot of it, between 1% and 10%, relative to the amount of water vapor in the coma. And this is in a comet that formed 4.5 billion years ago.
So it couldn't have been created recently.
The consensus is no. It wasn't being produced by sunlight breaking down water or other surface chemistry in the present day. The levels were too high and too consistent regardless of distance from the sun. The leading theory is that this molecular oxygen was actually incorporated into the comet's water ice structure way back when the comet first formed, trapped within the ice lattice in the incredibly cold, dense molecular cloud that predated our solar system. If true, it means this O2 is primordial, giving us a direct chemical sample of the conditions before the sun and planets even fully formed, a truly ancient relic.
So after those first couple of days, Philae went quiet. But hope wasn't entirely lost, was it? As 67P got closer to the sun on its orbit, maybe the sunlight would get strong enough to wake the lander up.
That was the hope, yeah. More sunlight, maybe enough power trickle-charging those secondary batteries to bring it back online. And for a little while, it actually worked. Between June and July 2015, as the comet neared its closest point to the sun, Rosetta started receiving intermittent signals from Philae again. It woke up.
Wow, so it came back to life.
Briefly. It sent back some housekeeping data, confirming it was alive and functioning, although very cold down around minus 35 degrees Celsius. Mission Control even managed to send up a few basic commands, mainly trying to get an instrument called CONSERT, a radar experiment that worked between the orbiter and lander, to run.
But they couldn't get a solid connection, not enough to do detailed science.
That was the heartbreaking part of the reawakening. To really upload complex new command sequences or download significant amounts of stored science data, they needed a stable, continuous communication link lasting at least 50 minutes or so. And they just never got it. The contacts were too short, too unpredictable, probably due to the lander's awkward orientation and the increasingly active, gassy environment around the comet interfering with the signal. The last confirmed contact was on July 9th, 2015.
And after that,
Oh, silence.
they kept listening for months, just in case. But nothing. Eventually, in July 2016, they had to make the tough call to permanently switch off the communication unit on Rosetta that was dedicated to listening for Philae. The little lander was officially declared lost again. But they still didn't know exactly where it was on the comet's surface, right? Which must have made interpreting that initial science data tricky.
Exactly. For almost 2 years, it was this mystery. They knew roughly the region, Mahamad, but not the precise spot. It was like the ultimate game of cosmic hide-and-seek, trying to spot this washing machine-sized lander, probably in shadow, on a dark, lumpy, rotating comet from orbit. But then, incredibly, on September 2nd, 2016, literally just weeks before Rosetta's own mission was scheduled to end, they found it.
No kidding. How?
Rosetta's high-resolution narrow-angle camera, OSIRIS, was doing detailed scans of the surface, and in one of the images, there it was, a little glint of metal, Philae, wedged tightly on its side in a dark, rocky crevice, just as the indirect evidence had suggested.
Finding it must have been a huge relief even that late in the game.
Oh, massive. Scientifically, it was vital. Finally knowing the exact location, the orientation, the surrounding terrain, it provided crucial context for all the data Philae collected during those first 60 hours. They could finally say, okay, this hardness reading came from this specific type of rock it was touching, or this temperature reading relates to this amount of shadow. It anchored the interpretation.
And then, with Philae found but silent, it was time for Rosetta's own final act. They decided not to just let it drift off or try another hibernation, but to end it with purpose.
A really fitting, poignant end, I think. The decision was made to perform a controlled descent, essentially a hard landing, onto the comet's surface itself. The goal wasn't survival, obviously, but to maximize the science return right up to the very last second. Use every last bit of fuel and instrument capability to get ultra close-up images and data during that final plunge. The date was set, September 30th, 2016.
A controlled crash, basically. How slow was that final approach?
Incredibly slow, deliberately so. They initiated the main descent burn about 14.5 hours before the calculated impact time. The estimated impact speed was only about 89 centimeters per second. Less than walking pace, really. Just a gentle touchdown, relatively speaking. The chosen impact site was in the Ma'at region, near Philae's resting place, and was named Sisset, linking back to Egypt, the original home city of the Rosetta Stone.
And the final pictures must have been amazing.
Absolutely stunning. The Osiris camera kept snapping pictures all the way down. The very last complete image transmitted back, just moments before impact, was taken from an altitude of only about 23 to 26 meters, maybe 75 feet. It shows incredible detail, features just centimeters across on the dusty, rocky surface. Then, right on schedule, the spacecraft's signal abruptly cut out as it hit the surface. Mission officially over. 12 years, complete.
What an ending. And the legacy. It wasn't just the science, was it? This mission really seemed to connect with people globally.
It absolutely did. It became a genuine media phenomena in a way few robotic space missions manage. Yeah. That Philae landing attempt, especially, just captivated everyone. You had the hashtag comet landing hashtag explode on Twitter and social media, huge public engagement, and ESA, the European Space Agency, did a brilliant job with outreach.
Yeah, those little cartoons.
The animated web series, Once Upon a Time,
yeah,
where they personified Rosetta as the wise older sister and Philae as the adventurous, slightly clumsy younger brother. That was genius. It made people feel emotionally connected to these machines exploring this alien world. Combine that with things like the composer Vangelis dedicating a whole album to the mission and the short sci-fi film Ambition that ESA commissioned. It really cemented Rosetta and Philae not just in the history of science, but in popular culture too. Hashtag tag tag outro.
So looking back at this deep dive, the key takeaways are pretty immense, aren't they? We learned comets aren't soft snowballs. They have these hard, icy cores under dusky surfaces.
We got the most detailed map ever of the complex organic chemistry simmering on a comet, the raw ingredients for life.
And we proved, albeit dramatically, that landing on these tiny low-gravity worlds is possible, even if sticking the landing is tricky.
And then you synthesize those two huge findings related to life's origins. First, finding glycine, a fundamental amino acid, formed abiotically out there.
Right.
And second, that crucial correction about the water. Realizing that 67P's water is actually isotopically compatible with Earth's oceans, putting comets firmly back in the picture as potential water delivery vehicles.
So what's the final thought we leave our listeners with? Staring back across 4.5 billion years, what does Rosetta tell us about our own origins?
Well, think about it. We now know that these ancient icy bodies, comets like 67P, they definitely carried many of the complex organic building blocks needed for life. And it now seems plausible they could have delivered a significant portion of Earth's water too. So perhaps we shouldn't just see them as leftover debris or dusty snowballs anymore. Maybe we should start thinking of them as incredibly efficient cosmic delivery systems, maybe even the ultimate cosmic incubators, packaging and transporting the essential chemical and aqueous ingredients that kick-started the whole process for life here on Earth. It certainly makes you want to look much closer at those other organic molecules they found, like acetamide and methyl isocyanate, and figure out exactly what role they might have played in that very early prebiotic soup. There's still so much more to decipher.
Welcome back. We often talk about, the big Atlantic storms we see now, Katrina, Maria, all tracked meticulously on radar. But today we're going way back to a time before all that. We're looking at a catastrophe so intense, it almost beggars belief. It didn't just cause immense suffering, it actually crippled powerful European navies during a major war.
We are talking about the Great Hurricane of 1780. It's often cited as, well, probably the deadliest single tropical cyclone we know of in the Western Hemisphere. And for this deep dive, we want to give you more than just the headline facts. Our mission really is to help you understand its sheer scale, yes, but also its huge historical and geopolitical weight. We're digging into the sources to give you a shortcut to grasping how this event was this perfect storm of meteorology, warfare, and absolute tragedy.
Let's start with that scale because the numbers, frankly, are mind-boggling, especially for the 18th century. What are we talking about in terms of human loss across the Lesser Antilles?
The estimates do vary a bit, which is understandable given the time, but the consensus points to somewhere between 22,000 and possibly 30,000 deaths just across those islands in the space of less than a week.
22 to 30,000.
Yeah. And to really let that sink in, think about this. The death toll from this one storm in 1780, it surpasses the combined total fatalities from many entire decades of Atlantic hurricanes recorded later.
That really does put it in a chilling perspective.
Yeah.
When we look at more recent history, is there anything even remotely comparable in the Atlantic?
Well, the storm that gets mentioned as the second deadliest is Hurricane Mitch, back in 1998. Devastating, no question. But, with Mitch, the figures are generally considered more precise because of modern reporting, modern infrastructure for counting, tragically. For 1780, we're relying on military dispatches, CARES records, colonial governors' reports, things like that. But they all paint this picture of just utter obliteration on a scale that's hard to comprehend even now. It was a true cataclysm.
And the timing. You mentioned war. We absolutely have to remember the backdrop here. This hits smack bang in the middle of the American Revolutionary War.
Exactly. Britain, France, Spain, the Dutch, they're all heavily invested, fighting tooth and nail for control of the Caribbean. These islands were incredibly valuable, the sugar colonies, major trade hubs.
So this storm wasn't just a tragedy unfolding in peacetime.
Not at all. It was, in effect, a major military event in itself. It acted almost like an independent force, inflicting damage that, honestly, no navy at the time could have possibly inflicted on another. You really can't untangle the story of this hurricane from the wider story of that global conflict.
Okay, let's dive into the storm itself, the meteorology, which, as you hinted, is tough because the official Atlantic Hurricane Database, the one we rely on today, only starts in 1851.
Right. So for 1780, we're working backwards from the damage reports, from eyewitness accounts, ship logs. It's meteorological detective work.
So what can we piece together about its path and origins?
We know it was first reported by a ship somewhere in the eastern Caribbean. This suggests it probably formed quite far out, maybe near the Cape Verde Islands, as many powerful hurricanes do. It then tracked generally westward, relatively slowly at first it seems, and really started impacting Barbados late on October 9th.
And Barbados. This seems to be where the accounts describe something truly off the scale in terms of intensity. The worst hit there on October 10th. What are the estimates for its strength when it hit Barbados?
Based on the descriptions of the destruction, and this is where historians like Jose Carlos Millas did some pioneering work analyzing those old accounts, the estimate is that it was likely a high-end Category 5 hurricane, possibly one of the strongest ever recorded hitting land. Millas specifically looked at the damage reports and suggested wind gusts could have reached maybe as high as 200 miles per hour. That's 320 kilometers per hour.
200 miles per hour. That's well into Category 5 territory, even by today's standards. How can we be even remotely confident about a number like that from reports written in 1780?
It comes down to very specific types of damage described, things that only happen with truly extreme winds. Millas pointed to accounts that said the hurricane literally stripped the bark off trees, completely bare.
Strip the bark off.
Yes. Meteorologists estimate you need winds well over, certainly approaching 200 mile per hour, to do that consistently to mature trees. And the anecdotal evidence matches this extreme intensity. People wrote that the wind was so deafening that people could not hear their own voices. Imagine that. Just a constant, overwhelming roar. Every house, every fort on Barbados was said to be destroyed. Not just damaged, destroyed. It basically flattened the island's infrastructure.
And there's one particular detail often cited that comes from a British admiral, George Bridges Rodney. It speaks volumes about the sheer force involved.
Yes. Admiral Rodney's report from Barbados is probably the single most astonishing piece of testimony. He reported that the winds were so powerful they picked up heavy cannons. These are large iron cannons from the coastal fortifications weighing several tons each.
Right, massive things.
Massive. And the wind lifted them and carried them reportedly a distance of 100 feet.
Lifted and carried them 100 feet.
That's what he reported. Lifted into the air. Think about the physics of that. The energy required to take tons of iron and just toss it like driftwood. That detail, more than almost any other, tells you this wasn't just a storm. It was something else entirely. The atmosphere itself becoming this destructive engine of unimaginable power.
Wow. Cannons flying 100 feet. Okay, so this This monstrous force then moves on from Barbados, heading northwest. And this is where the impact on the war really comes into sharp focus, isn't it? It tracks past Martinique, St. Lucia, St. Eustatius, all strategically vital islands being fought over.
Precisely. And it hit both the British and the French fleets sheltering in the area, hard. The storm showed no allegiance, obviously. It dealt crippling blows to both sides, fundamentally changing the naval situation in the Caribbean and, by extension, impacting the American Revolution.
Let's break that down. First, the British. What did this storm do to their naval strength right at that critical moment?
It was a major blow, a significant weakening of their grip on the sea lanes right when they needed them most. We know fleets under Vice Admiral Peter Parker and Rear Admiral Joshua Raleigh were caught. The losses were substantial. 3 frigates were lost. HMS Blanche just vanished, presumed foundered with all hands. HMS Andromeda and HMS Laurel were wrecked. Even more critically, they lost 2 ships of the line. These are the battleships of the era HMS Thunderer and HMS Stirling Castle. Gone. Plus, another 7 warships were dismasted, basically knocked out of action until they could get major repairs, which wasn't easy or quick back then.
Losing 2 ships of the line outright, just like that. In 18th century terms, that's a huge loss of strategic power, isn't it?
Oh, absolutely massive. Ships of the line were the capital ships, the ultimate expression of naval power. They took years to build, vast resources, huge crews, losing 2 instantly, along with frigates and damaging others. It's not just losing firepower, it's a logistical nightmare. It hamstrung British naval operations in the region for a crucial period. Suddenly, they're facing the French with significantly reduced capacity, purely because of the weather.
And the French. They were hit hard too, though perhaps differently.
They were. A large French fleet, about 40 ships, was anchored off Martinique and got hammered. Interestingly, they only lost 1 warship, the frigate Junon. But the human cost, particularly among soldiers being transported and on the island itself, was enormous. Several hundred military personnel died. And the civilian toll on Martinique was catastrophic.
Right. Let's talk about that island-by-island impact, because it connects those big death toll numbers to specific places. Martinique sounds like it was particularly devastated by water.
Yes, the storm surge seems to have been the big killer there. Reports estimate a surge of maybe 25 feet, that's over 7.5 meters, hitting the main town, Saint-Pierre. It essentially washed the town away. Sources say every single house in Saint-Pierre was destroyed. The death toll there alone is estimated at around 9,000 people. Just imagine that wall of water.
Unbelievable. And St. Lucia, another key island.
Equally horrific. Around 6,000 estimated deaths there. Admiral Rodney's fleet was actually sheltering in the harbor at Port Castries, St. Lucia, and experienced incredibly rough seas and wind. And here's another one of those almost surreal details. One of Rodney's ships was apparently lifted by the waves onto the shore and smashed into the city's hospital, destroying it.
A warship destroying the hospital.
Gives you a sense of the forces involved, doesn't it? And much like Saint-Pierre, the capital of Port Castries was basically wiped out. The reports claim only 2 houses were left standing in the entire town. Whether it was the surge like in Martinique, or the sheer wind force like on Barbados, or a combination, the outcome on these islands was terrifyingly similar. Near total destruction and societal collapse.
And this level of destruction wasn't just confined to the main French or British bases, right? Other islands suffered terribly, too.
Absolutely. Look at St. Vincent, for instance. Not perhaps the primary military focus, but still devastated. Reports say 584 out of the 600 houses in the capital, Kingstown, were destroyed. It wasn't just isolated damage, it was a swath of near-total annihilation across island after island that lay in the hurricane's path.
So after tearing through the Lesser Antilles, where did the storm go next? It still had a long journey ahead of it.
It did. After hitting Guadeloupe, it seems to have tracked northwest, running parallel to the southern coast of Puerto Rico. It actually made landfall there, near Cabo Rojo, on October 14th. Then it moved through the Mona Passage between Puerto Rico and Hispaniola, causing damage in eastern Santo Domingo, what's now the Dominican Republic. After that, it curved northeastward out into the Atlantic, passing about 150 miles southeast of Bermuda. Incredibly, it was last observed way up near Newfoundland, Canada, around October 20th. Just shows the immense scale and duration of the system.
A truly vast track. And it was still causing significant damage days after hitting Barbados, impacting Spanish territories like Puerto Rico and Santo Domingo.
Definitely. The reports from southern Puerto Rico, places like Cabo Rojo and Lajas and eastern Santo Domingo, confirm it was still a potent, destructive force even days into its life cycle. No escape along that path.
Which brings us neatly to its other name, the one used particularly in Puerto Rico, Hurricane San Calixto. This touches on how people remembered and named these events before modern conventions.
Right. It's a fascinating window into cultural memory and, well, practical record keeping before formal meteorology. In Puerto Rico, there was a long-standing tradition, apparently dating back to Columbus's time, right up until the mid-20th century. They named hurricanes after the Catholic saint whose feast day occurred on the day the storm, specifically the eye of the storm, made landfall on the island.
So because this hurricane made landfall in Puerto Rico on October 14th,
Exactly. October 14th is the feast day of Pope Calixtus I, who is San Calixto in Spanish. So the storm became locally and enduringly known as Hurricane San Calixto. It was a really effective system, you know. It gave people a clear, shared reference point to talk about specific historical disasters without needing detailed meteorological charts or anything.
a powerful mnemonic, tying the natural disaster to the shared cultural calendar, the religious calendar. And we see this with other famous Puerto Rican hurricanes, too.
We do. The San Ciriaco hurricane of 1899, the San Felipe Segundo hurricane of 1928, major, devastating storms remembered by their saints' day names. This tradition only really faded when the U.S. Weather Bureau started using female human names in 1953, and then later the alternating male-female lists managed by the World Meteorological Organization from 1979 onwards took over globally. But it's a great reminder that naming conventions evolve, and local traditions often fill the gap, providing vital historical continuity.
Okay, so let's try to pull the threads together from everything we've discussed. If we synthesize the key takeaways from the sources on the Great Hurricane of 1780, what stands out? We have this almost unimaginable death toll, perhaps up to 30,000. We have accounts of physical intensity so extreme it could toss cannons around.
Literally toss cannons, yeah. And crucially, the timing. Hitting right in the middle of the American Revolution, massively disrupting both British and French naval power in the Caribbean theater at a critical juncture. It was a geopolitical event delivered by nature.
So, wrapping this up, what's the final thought we should leave with you, the listener, to chew on?
Well, here's something really intriguing. The Great Hurricane of 1780, this monster storm, wasn't alone that season. The historical records actually show that October 1780 was an extraordinarily brutal month. There were two other distinct, deadly hurricanes that also struck the Caribbean region in that same month.
3 major hurricanes in 1 month.
3 major deadly hurricanes. We have this cluster of extreme events documented before the official hurricane database even begins in 1851. So the question this raises, the thing for you to mull over, is this. Given this documented peak of devastation in 1780, what does it suggest about the true, unrecorded history of extreme weather in the Atlantic? How many other seasons like 1780 or storms like the Great Hurricane occurred in the centuries before we had systematic records? It makes you wonder if our modern baseline for intense hurricane activity perhaps misses a much longer and maybe more volatile history. It really suggests the documented record might just be scratching the surface of what the Atlantic is truly capable of. Something to think about next time hurricane season rolls around.
Today, we are digging into one of the most, well, persistent and often misunderstood concepts in political economy, laissez faire.
It really is. It's a French phrase, of course, that somehow survives centuries of, intense debate. Literally, it translates to let it them do.
Right, but it's usually shorthand for that longer sort of foundational motto, laissez faire, laissez passer.
Exactly, meaning roughly let do and let pass. Let things happen, let things move.
And our mission, really, in this deep dive is to show you that this simple phrase, which describes an economy supposedly free from any government intervention, no subsidies, no regulations, no tariffs.
Zero interference.
It has a history that's way more complex, even contradictory, than that simple definition might suggest. We're going to peel back the layers. Where did it come from? How was it actually applied? And, well, why is it still such a lightning rod today?
Yeah, and to really get it, you have to start with the philosophy behind it all. I mean, laissez-faire rests on these core principles that, while they feel very Western Enlightenment, but they're actually pretty radical when you unpack them.
Like what, specifically?
Well, first, the idea that the individual, you, me, everyone, is the basic, almost sacred unit of society. Second, that this individual has a natural and inherent right to freedom that shouldn't be touched.
Okay.
And maybe most importantly, this belief, and it is a belief, that the physical order of nature, the world itself, is this harmonious, self-regulating system.
And government interference can only mess it up.
That's the core idea. It can only disrupt that natural harmony.
Okay, and here's the hook right away, because you just said it sounds so European, so Enlightenment. But where does this rumor come from about Chinese philosophical origins? That seems kind of out of left field.
It's an incredible little historical footnote, isn't it? One of the first French guys to really popularize the concept, a man named Vincent de Gournay, he apparently adopted the core idea, or was at least heavily influenced by Chinese philosophy, specifically Taoism.
Wow.
Yeah, he drew from this concept called Wu Wei, that's W-U-W-E-I, and it basically means non-action or non-intervention.
So the idea that the best way to govern is, well, not to govern.
Yeah, exactly. Let things flow naturally. It's fascinating that this supposedly Western idea might have these Eastern roots.
That really sets things up nicely. So let's trace the actual phrase back to that famous French origin story. It supposedly takes place, what, late 17th century?
That's the one. We're talking France under the height of mercantilism, where the state was heavily involved in controlling and directing pretty much all trade.
Total control.
Pretty much. And you have the powerful Controller General of Finances, Jean-Baptiste Colbert. He was basically the king's money man meeting with a group of French businessmen. This is around 1681. And Colbert, being a good mercantilist, wants to figure out how the state can help boost French exports, through support and planning. So he asks them, point blank, how can the state best help you promote commerce?
And their leader, a guy named Monsieur Legendre, gives this incredibly blunt, short answer that basically becomes the slogan for the whole doctrine.
He just says, Laissez faire.
Leave it to us. Or maybe even let us do our thing.
Exactly. Just get out of the way. Stop interfering.
And this idea, this phrase, it really catches fire later in the 18th century, right? With that group called the physiocrats.
Yes, the physiocrats were key. If you actually break down their name, physiocracy, it means rule of nature. They had this core belief that all real wealth came purely from the land, from agriculture.
Because that's natural production.
Right. And since they saw nature as operating harmoniously, they figured the economy should too. It followed logically for them.
So because they believed in this natural order of liberty, their big argument was that if individuals just chase their own economic self-interest,
their selfish interest, yeah,
they'd somehow unintentionally end up contributing to the overall good of society.
Precisely. The invisible hand idea, even before Smith really popularized it. So for the physiocrats, the state's job was super limited. Basically just protect property rights, protect personal freedom, and otherwise step back completely.
Okay, but this theory got put to the test pretty quickly, didn't it? And not in the good way.
No, not at all. It ran smack into human suffering.
Yeah.
King Louis V, who was, influenced by these physiocratic ideas, decided to try it out. In 1754, he abolished all the tolls on grain transport within France.
Yeah. A move towards pure laissez-faire, trying to make things more efficient.
That was the goal. But then disaster struck. A really poor harvest hit hard in 1768.
Oh boy. So wait, you're saying the very first major policy experiment based on this let it be idea,
Yeah.
It failed. Spectacularly.
Absolutely spectacularly. Because the merchants, now completely free to sell grain wherever they could get the highest price, remember, no regulations, no export controls, they started exporting grain for huge profits, selling it abroad, while people in France were facing mass starvation.
Wow. So the ideology, the theory, just trumped basic survival.
It did in that case. Abstract trade theory over human welfare. It led to widespread riots, total social unrest, and the government was actually forced to revoke the edict in 1770. It was a very harsh, very public lesson on the potential downsides, the potential cruelty of the doctrine when applied rigidly.
It's also really important to realize, though, that while the phrase laissez-faire was maybe crystallizing then, the underlying idea, the legal concept of the individual and their property being paramount, that wasn't new, was it?
Not at all. That's a crucial point. You can trace the idea that the state shouldn't really meddle in private commerce way, way back, all the way to Roman private law, actually.
Really?
Yeah.
Roman law?
Yeah, between the 1st and 3rd centuries AD. That legal tradition really developed and established the theory of absolute private property rights and the freedom to trade, the freedom to make contracts. So in a lot of ways, laissez-faire was just sort of reviving or maybe repackaging this very deep-seated Western legal heritage of individualism.
Okay, so the 18th century then brings us to Well, the person everyone associates with this idea, Adam Smith.
Mhm.
This is where laissez-faire really starts to take shape as the defining philosophy of modern capitalism, right?
Absolutely. Adam Smith is central. His book, The Wealth of Nations, published in 1776, it wasn't just an economic blueprint. Smith saw it almost as a kind of moral program.
A moral program. How so?
He believed this system would restore what he saw as the natural law rights of individuals, and by doing that, it would unleash huge potential for national prosperity, for growth. It was about freedom and wealth creation.
But here's a fascinating little detail, a linguistic point you mentioned earlier.
Uh,
While Smith is like the philosophical godfather of non-intervention,
He never actually used the French phrase laissez-faire himself, not once in The Wealth of Nations.
really? So what did he use?
He used a different, now equally famous, metaphor, the invisible hand. It's a concept he actually borrowed, or at least was influenced by, from an earlier writer, Bernard de Mandeville, and his Fable of the Bees.
Ah, okay. And the invisible hand describes.
It describes those unintentional but positive social and economic benefits that just emerge naturally when millions of individuals simply pursue their own self-interest in the marketplace. It's the idea of spontaneous economic self-organization.
So Smith provides this powerful intellectual framework. But when this framework, this doctrine, gets tested by a real crisis, it sometimes revealed, well, a shocking kind of rigidity, didn't it? We see this very starkly in Britain during the Irish famine.
Yeah, the mid-1840s. That period, especially around 1847, is probably one of the most chilling examples of pure laissez-faire ideology put into practice. Despite catastrophic potato blight, mass starvation, people dying in the streets, many prominent British leaders, thinkers, commentators, they clung rigidly to the belief that the state must not intervene in the market. Providing food aid, they argued, would just distort the natural mechanisms of supply and demand. It would create dependency.
And that infamous quote from the founder, the economist James Wilson, really captures that brutal logic.
It really does, Wilson wrote quite starkly. It is no man's business to provide for another.
Wow.
It's a shocking statement to modern ears, but it reflects just how deeply that ideology had taken root. This idea that abstract market mechanics were somehow more sacred, more important than preventing mass death, and that strict adherence ensured hundreds of thousands perished even while food was technically available elsewhere, including in Quebec itself.
Just devastating.
Yeah.
Yet, at roughly the same time, there was another big push happening in Britain related to free trade, championed by people like Richard Cobden and John Bright, the Manchester Liberals.
That's right. This was the campaign against the Corn Laws. These were basically high tariffs, taxes on imported grain.
Designed to keep prices high.
Exactly. Primarily designed to protect the incomes of the wealthy landed aristocracy by keeping bread prices artificially high for everyone else, especially the working poor.
So the opposite of free trade.
Totally. And the Manchester Liberals fought hard against this. The repeal of the Corn Laws in 1846 was seen as a massive victory for the spirit of free trade, for laissez-faire principles in a way. It helped open up global markets.
But sadly, it came too late to really help with the famine unfolding across the Irish Sea.
Tragically, yes. The timing was just off. The repeal was a landmark moment for free trade theory, but it couldn't stop the immediate humanitarian disaster in Ireland that was happening partly because of a rigid adherence to another aspect of the same doctrine.
Okay, let's shift gears now and cross the Atlantic. There's this common perception, I think, that American economic history is basically the ultimate laissez-faire success story. Pure capitalism, minimal government, right from the start.
Yeah, that's the popular image, but the sources we looked at, they really challenged that simplistic view quite strongly.
How so?
Well, the reality seems to be that the vast majority of American classical liberals, especially in the 19th century, they did not interpret laissez-faire as meaning absolutely no government intervention ever.
They weren't purists.
Not really. They seem to have been much more pragmatic. They were actually quite comfortable using targeted state action when they thought it served the national interest, particularly when it benefited producers and promoted commerce.
Okay, so give us some examples. What kind of government actions are we talking about that seem to contradict that pure hands-off idea?
Oh, plenty. Think about the federal government setting up the Patent Office way back in 1802. That's direct government action to protect inventors' monopolies, essentially.
Right, incentivizing innovation through state protection.
Exactly. Or the Survey of the Coast, started in 1807. That was the government actively mapping the coastline to make shipping safer and commerce easier. That's not exactly letting things be.
And these weren't just small things, right? We're talking about massive federal involvement later on, too.
Huge involvement. Think about the enormous land grants and subsidies given to railroad companies to build the transcontinental railways. That's direct government support on a colossal scale.
Or things like internal improvements canals. Roads often funded or supported by the government. And what about the big banking debates?
Absolutely central. The creation and the intense political battles over the first Bank of the United States and later the Second Bank. These were powerful government-chartered institutions designed specifically to stabilize the currency and actively shape the national economy.
So the American interpretation of let do often seems to have meant let the government help the people doing things.
That captures it pretty well, I think. And this tendency towards what we now call a mixed economy, a blend of private enterprise and government intervention, it actually accelerated after the Civil War.
Right, you see protectionism really ramp up, don't you? With huge tariffs.
Massive tariffs. Things like the McKinley tariff, the Dingley tariff, later on these, were setting historically high barriers against imported goods, specifically designed to shield American industries from foreign competition. That is the absolute opposite of laissez-faire free trade.
And at the same time, government regulations started to expand too. It wasn't just about promotion anymore, but also control.
Exactly. You get the Interstate Commerce Act in 1887 aiming to regulate the powerful railroad industry. Then the Sherman Antitrust Act in 1890 trying to break up monopolies. So the idea of this pure, frictionless, unregulated market that the early physiocrats dreamed of, by the late 19th century in America, it was clearly long gone, if it ever truly existed in practice.
Which brings us closer to the modern era and thinkers who do advocate for that pure, uncompromising version, like Ayn Rand.
Right. Ayn Rand, the objectivist philosopher, founder of that whole school of thought based on rational self-interest, she represents that modern, hardcore advocacy for pure laissez-faire.
How did she define it?
For Rand, it was crystal clear. She defined it as the abolition of any and all forms of government intervention in production and trade, the separation of state and economics. Full stop.
So not just limited government, but basically no economic role for government whatsoever.
Precisely. And for her, this wasn't just about efficiency or practicality, it was a moral imperative. She viewed pure laissez-faire capitalism as the only moral social system because, in her view, it was the only one that fully respected and protected individual rights without any exceptions or compromises.
Okay, so Rand represents that capitalist extreme of non-intervention. But here's where things get really interesting, maybe even kind of mind-bending. The idea of pure non-intervention, getting the state out of the economy, it's also been claimed by thinkers on the political left.
It's absolutely fascinating, isn't it? This is where you encounter concepts like left-wing laissez-faire or sometimes free market socialism or free market anti-capitalist.
Wait, free market socialism, how does that even work? Aren't those complete opposites?
It seems like it on the surface. But thinkers in this tradition, people like Benjamin Tucker back in the 19th century, or more contemporary writers like Kevin Carson, they make a very different argument. They argue that a truly free market, what they often call a freed market, emphasis on freed from state distortion, would actually be inherently anti-capitalist.
Okay, I need you to unpack that. How can getting rid of the state lead to socialism or anti-capitalism?
Their argument hinges on how they see current corporate power. They argue that the massive corporations and concentrated wealth we see today are not the natural result of free competition. Instead, they see them as creatures of state intervention.
State intervention creating corporate power.
Exactly. They point to things like massive corporate subsidies, government bailouts, state-enforced monopolies like intellectual property laws, especially patents and historical land appropriations. They see all these as artificial privileges granted by the state that allow corporations to avoid true competition and extract excessive profits.
So their logic is, if you remove all these state interventions and privileges,
then true, fierce competition would finally flourish, barriers to entry would fall, and without state protection, they believe these large hierarchical corporations couldn't survive. Power would decentralize, maybe leading to more worker cooperatives, smaller enterprises, a system that looks much more pro-labor and anti-capitalist in the conventional sense.
wow. So it's incredible. You have right-wing objectivists and these left-wing market anarchists both fundamentally wanting to abolish state intervention in the economy.
Yes, the mechanism get the state out is surprisingly similar.
But they predict radically different outcomes. One sees pure capitalism, the other sees something closer to socialism.
It all comes down to whether you think current inequality is caused by too little market freedom or by market distortions created by the state. It's a fundamental disagreement about the nature of the problem.
Okay, but setting aside these more radical interpretations, the mainstream view of laissez-faire has faced some heavy criticism over the years, right? Starting with Keynes.
Oh, absolutely. John Maynard Keynes, probably the most influential economist of the 20th century, was deeply critical of laissez-faire as a rigid doctrine. He famously argued that the decision whether to rely on a market solution or to use state intervention, well, it must be determined on a case-by-case basis.
No universal rule, just pragmatism.
Exactly. For Keynes, blindly applying laissez-faire everywhere was just as irrational as blindly applying state control everywhere.
Yeah.
You have to look at the specific situation.
And there was also Karl Polanyi, who had a different kind of critique, more historical or sociological.
Yes, Polanyi, in his book The Great Transformation, argued that the very idea of a purely self-regulating market, completely separate from social concerns, is actually an aberrational, unnatural phenomena.
Unnatural.
Yeah. He suggested that markets, left entirely to themselves, tend towards social disruption, instability, and commodifying things that shouldn't be commodified, like labor or land. He believed society inevitably pushes back, imposing rules and regulations to protect itself from the destructive tendencies of unregulated markets.
Which kind of leads us to how the term is often perceived today, doesn't it? In modern economics, or just in general conversation, laissez-faire often seems to carry a pretty negative connotation.
It definitely can. It's often used almost as a synonym for raw capitalism or cutthroat capitalism. It can imply kind of disregard for broader social values, things like quality, durability, environmental sustainability, worker safety, basic human well-being.
Because the pure doctrine prioritizes profit and efficiency above all else.
That's the implication. The critique is that pure self-interest, without any external checks or balances or shared values, doesn't provide a mechanism for accountability for those wider social costs. Profit becomes the only metric.
And we really need to bring this full circle back to Adam Smith himself. Because even the supposed father of the system, he wasn't entirely comfortable with all aspects of capitalism, was he? He had his own moral concern.
That's incredibly important. Smith was very clear, especially if you read his other major work, The Theory of Moral Sentiments, which actually came before The Wealth of Nations.
What did he say there?
He essentially argued that the entire economic system described in The Wealth of Nations was fundamentally dependent on a pre-existing moral framework within society. Things like empathy, justice, fair play, rule of law. He believed society would utterly collapse without a shared morality and functioning laws.
So he never intended for his economic system to operate in some kind of moral vacuum. The invisible hand needed a moral glove, so to speak.
That's a great way to put it. He saw morality and law as the necessary foundation upon which the market could then function effectively and beneficially. He wasn't advocating for pure amoral self-interest running rampant.
So what we've really uncovered here is that laissez-faire isn't just some dry economic policy setting. It's tangled up in centuries of philosophical debate. It touches on the true nature of individual rights, the proper role, if any, of government, and even leads to these completely paradoxical definitions of what a free market actually is. Is it inherently capitalist? Or could it be something else entirely if the state truly stepped away?
It leaves us with a lot to think about. And that really leads us to our final thought for you, the listener, to consider. If you take philosophers like Thomas Hobbes, who argued centuries ago that life without laws and government, the state of nature, is inherently solitary, poor, nasty, brutish, and short.
Right, the idea that we need government for basic order and safety.
And if you also take Adam Smith's insistence that his whole economic framework depends on having shared moral values and enforceable laws already in place as a prerequisite, well, it raises a really fundamental question, doesn't it?
Which is?
Can the total abolition of the state and all its interventions, which is the purest definition of laissez-faire, whether from the right or the left, can that ever truly lead to the harmonious and self-regulating system that its proponents imagine? Or must some level of government intervention, however minimal, always be necessary simply to establish and secure the essential moral and legal foundation upon which any functional market, any complex society has to be built in the first place?